So let us move on and talk about restrictions and possible ways of improvement in current neural networks technologies. And it will be continued by Maxim Panov, who will speak about uncertainty estimation. Maxim, the floor is yours.
Максим, мы вас не слышим.
Maxim, could you turn on the mic, please? Yes, thank you. Thank you very much, Anton. My name is Maxim Panov, and I work in Skoltech, and I lead a group of statistical machine learning, and I work there as also a senior teacher, senior professor, and I would like to thank the organizers for the opportunity to speak here. I believe that the topic of my presentation logically belongs to the theme of our session, because opportunities to assess the confidence in your predictions, in your actions, to make a decision that you cannot do something because you are not capable of that, is a truly natural part of a natural intelligence of a human being. Let us discuss what neural networks can tell us, can help us with. We all know that a neural network enables us to make a prediction, and it predicts pretty well. For example, it can solve the problem of discerning cats and dogs on pictures, on images, but it would be great if a neural network at the same time could assess its certainty of prediction. For example, when it receives an image that it has never seen before, something different or something complex, like this cat and dog together that I have on this image on the slide, so that it should be able to reject, to predict. And there are different assessments of probability, that is Bayesian optimization, active learning, adversarial examples detection, and a simple task of the ability to reject, to predict. You can say that neural network is by default giving some probability and confidence in the prediction. And we can see that in binary classification, and we can see that certainty in multi-class classification. So assessment of confidence and uncertainty will be seen as a certain value. It would have been great, but more neural networks are not well calibrated. If you have a look at a neural network and see the objects that it classifies with P0, for example, 0.7 certainty, it does not mean that the neural network at these objects with a probability of 0.7 will give less errors. Furthermore, it will be not like that. There will be large discrepancies. And usually, a plot like this is drafted, like we have on the right-hand side on my slide. And on x-axis, that is the certainty of the model, and on y-axis, that is the accuracy. And we can see that the model overestimates that strongly. So the ideal chart should go on a diagonal line, and we are much lower. This issue was seen some years ago, and it has been solved to a certain extent. For example, you can take a test sample and you work on the output probabilities of the neural network that are called temperature scaling. They enable to solve the problem in the following way. So here you can see that the error was large in predicting the probability, and if we have the temperature scaling correctly, we can see that the chart will follow this diagonal line that it should. So once we have calibrated it, have we solved the problem? Not exactly, because there are a lot of task set where calibration cannot be applied. For example, here I have a unidimensional sign and I have only one input variable. In black, you can see the prediction of the neural network, and the binary classification gives the probability of the first class. So here you can see probability 0, 0.7 on the left, 1 to the right, and all the probability of the sampling was here in the gray line, with the gray dotted line. And I, for example, would like to predict in the red dotted line. This is very far from the training sets. And as for the training data sets, we do not have an idea what is happening there. Therefore, the calibration and probability notions cannot be applied in this area, because whatever class possible can belong there, one of the two that we have considered or something totally different. Therefore, a task is posed to detect objects that are beyond the distribution or out of the distribution. A couple of words about the formalities to be able to understand what kind of problems of this type exist. In machine learning, data usually proceed from some distribution, like signs X and matrix Y. We can factorize this distribution differently. I will not give you detail here, but I will tell you the following thing. If at the moment of testing the data distribution stays the same as during the training, everything is good. For example, we can use calibration methods and the correct probability will be predicted. However, if at the moment of testing the distribution does not equal the one of training, then the problem occurs. Inequality of the distribution can be different. There can be difference in axis distribution or in output variable. For example, some class has sharply increased, or they can be an extreme when during the prediction objects of new classes turn up. That is a standard thing, for example, in face recognition. It turns out that out of distribution objects are something that neural network are non-sustainable at all. For example, on the right-hand side, you can see pictures that are pretty abstract, but they are recognized as a king penguin or remote control. And the alternative assessment to uncertainty estimation can be solved differently. One of them is disagreement. When you take several models and then you see if these models agree in prediction in some point, then you can be confident on that. If they diverge, then it is a complex object and there is no certainty in prediction. And there can be various options of this kind of approach. There can also be ensembles where you take many models and they are widely used, and the standard and the best running way is to train many similar neural networks simply using different initializations, so different initial values of parameters that will get to the output parameters. That is a simple maybe thing, but it is too cumbersome because you have to train models several times and you have to run this several times. It is all very long. That's why the literature has proposed many options of how to speed up ensembles. I will briefly talk about one of them, which is called Monte Carlo dropout. We all know dropout as a regularization method for neural networks. But some years ago, there was an interesting observation that dropout is dropping out neurons during the training. And it was noticed that when a neural network is already trained, we can still drop out neurons, and then every mask of this drop out that turns up creates a separate neural network for us. Therefore, in one architecture, we receive a whole ensemble. And this method is widely and successfully used and can be found in dozens of papers. However, all these methods based on ensembles still face an issue. Here, for example, there is a MNIST data set in two-dimensional latent space of autoencoder, and the black shows the degree of confidence, and there are very light areas, means that we go away from MNIST into the area of unknown pictures, but still the certainty we can see is pretty good. That is not correct. We need to fight that. One of non-conventional new approaches that has been recently used is as follows. You use your trained neural network not as a predictor, but as a signs extractor. For example, you have these instances, and then you receive embeddings, and then a very easy idea is applied, like let's believe that embeddings geometry reflects the geometry of initial images, and if some new test object in embedding space is far from the training set, then it means that that object is out of distribution. This idea was implemented in a series of papers. One of the links is present here in this slide, and it was shown that pretty good uncertainty estimation can be received. For example, if some ensemble shows an estimation on the picture on the left-hand side, so in yellow there is this certainty, and we are pretty certain, very far away from the set, the shown algorithm give very good results. For example, here you can see that in blue, right? We are not certain going away from the core. And in our work, we have put forward a method, non-parametric uncertainty quantification, that helps to improve uncertainty estimation. That is composed of two parts. One of them is uncertainty based on probabilities, and the second part, without the full formula here, but it is important that it is reverse proportional to marginal density of X. So X will have large values where probability is low, and all these probabilities can be assessed with nuclear methods in space of embeddings. We have run certain experiments on that to our method and received an interesting result. The first result that I would like to share with you is the following. We've taken a neural network trained on MNIST dataset, and then we additionally looked at a less well-known SVHN dataset, that is a number of blocks recorded to a low resolution camera, and we concatenated this, and then we sorted the images according to their uncertainties, and asked the network to say what objects it is confident in, what not. And here you can see the share of SVHN images included into consideration versus annotated MNIST. The ideal algorithm should give this like arrow from 0 to 10,000, and then up from 10,000 to almost 20, and that works not bad. And our approach, NUQ, works ideally. Then we complicated the task. We rotated the pictures at random angles from 9 to 95 degrees. And here you can see simple algorithm just broke down. You can see that the curves on red and green dotted lines are just guessing, and our method works well, but a little bit worse than in the previous picture. And here I would like to show you an interesting picture. All these images are from our NIST dataset. They are different artistic images with classes like in our ImageNet. And here, in top layer, there is low uncertainty images, then mid uncertainty, then low uncertainty. And we can see that the objects actually follow the human idea of whether they look like real objects or not. For example, this brilliant cardboard Scorpio is pretty good. It looks like a real one. We've also run some experiments of quantitative character to show that our method in big data like ImageNet works pretty well. And summing it all up, I would like to say that the task of detecting uncertainty and filtering objects of non-distribution is very important, and I cannot say that it is well solved currently, and the whole global community is now actively working to solve it. Thank you very much for your attention. I have finished my presentation. Thank you, Maxim. We have received a question. Do you think it's right to propose to go away from neural networks to systems based on probability logics like NARS system and Bayesian systems, new networks, and VTIV developments from Novosibirsk? So there is this probabilistic estimation that is by design, so to say, embedded, whereas in neural networks we have to run additional experiments and tricks to take out this probability uncertainty. Thank you very much. I myself am a fan of Bayesian networks, and we are developing them in my group actively. I believe that it is a promising area and correct one, and I believe that probabilities, Bayesian approach and alternatives have to be embedded ideally in the initial stage of the model architecture. But the only issue here is that, as a rule, there are computational difficulties that turn up. And that is why this area is a little bit far from practical application. All the success of Bayesian neural networks that I know of as of now are pretty childish, and they are far from real practical applications, apart from several large examples of success. So I believe this area is really very interesting, and I believe that in the near future there will be huge breakthroughs in Bayesian neural networks. Thank you very much, Maxim.